Hello and welcome. Today I wanted to show you an application of near-infrared spectroscopy, which is the search for life on exoplanets. First, one slide about what is NIRS. This slide can be found in an earlier presentation. And then this example NIRS in the planetary atmosphere of the K2-18b planet. NIRS is looking for features of molecules, and the problem is about NIRS is that it's harder than visible light spectroscopy because often the spectral lines are wide and overlapping, so it's hard to interpret the spectra. We will see this in the example. It also includes shortwave infrared, so NIRS often the definition is not sharp, or yes, the wavelength you look at goes to 2.5 microns or so. So often it's including modeling, and you model components of a gas and then you compare it with the spectrum. So it's quite hard detective work, and we will see this in the example. So how do you look for life in planets that you can't actually see as a resoluted planet because they are much too small and too close to their mother stars? These days, most exoplanets have been found when they pass over their mother stars. So what you do is you take two spectra, one of the star without the planet and one of the star with the planet in front. And then if you see differences, reliable differences between these two spectra, you assume that it's due to the planet that is moving in front of the stars. And you know that because the observatories that find these stars often work with these occultations. So for example, the Kepler satellite that is shown here to the right is actually you could say a staring satellite. It's stared just at one part of the sky and looked at dips in the brightnesses of stars. And if you have regular dips, then you can assume something must go around this star. And often then you look at the mass with another method, and if you find that the mass of this body that circles around the star is not too high, you assume it's a planet, despite in most cases you're not able to see the planet, not even with JWST. So in the example that we're looking at today, the K2-18 star, this is a red dwarf star of the spectral type M 2.5 Roman 5. As you know, M is the latest regular star type in the Hertzsprung-Russell diagram. So the sun would be a G, and then it's just K and M. And M normally are very small stars, dwarf stars. And this dwarf star is 124 light years from Earth. And the planet was discovered by the Kepler satellite, and it orbits the star every 33 days roughly at a distance of 21.4 million kilometers. So it's roughly a seventh of the distance from the Earth to the Sun. So the planet is very close to the star. It's easier to find these planets with this method. And the mass is 8.6 times the mass of Earth. The radius is also larger than the radius of Earth. So it's a relatively large planet compared to the mass of the star, which I haven't shown you. But it's probably not a very heavy star. And the density is 2.67 grams per cubic centimeter. The density is often the only thing that you have to decide what type this planet is. And then they are more or less divided into Earths or super Earths or Neptunes or Jupiters, more or less, according to the mass they have and according to the density. So if I have a planet that is just 1 gram per cubic centimeter, it's most likely a gas planet. And then an icy planet, and if it's really, really heavy, 5 grams per cubic centimeter or so, it must be a full metal planet. And 2.67 is somewhere in between. Could be a silicate, a stony planet, maybe with an atmosphere, maybe without, but it turns out this planet has an atmosphere. And people thought it may be a Hycean planet, and this is a term for a planet with a large watery ocean surrounded by a hydrogen-helium atmosphere. And it's an important planet because it orbits its star in the habitable zone. What does habitable zone mean? You can calculate the irradiation on this star, on this planet, because you know the brightness of the star and you know the distance from the star to the planet. So you can say average temperature. Of course, this depends on the albedo and on the how strongly the atmosphere can keep the warmth together. So the greenhouse effect on these two things, but you can just assuming an average atmosphere or no atmosphere at all, you can say if there's water, it should be in the liquid range. So it's not a very cold planet, and it's not a so hot planet that all the water has gone away, cooked away. But the Hycean, we're not sure yet, as we will see later. Hycean planets are also easy to measure because they have large atmospheres and the gases can be found relatively easily. So now I'm reporting a series of studies, and they all have the same first author, which is Madhusudan. And the first paper came out in 2023, and they made this modeling based on the spectrum, that they obtained the spectrum with the NIRS instrument, and this NIRS-spec instrument from the JWST, which is, I think, the best telescope for that at the moment. But you can see there is a full model with assumed gases, and there are just, if you fit just the gases alone, you can see what happens, and this has been color-coded. And in the end, you have this very complicated part of the spectrum where everything is very close together. So, yeah, and based on this, based on the second paper that these authors said, what we found for sure in this atmosphere with the JWST data was methane. And this 5 sigma means it's really, really statistically very safe data. For the methane, we found CO2 with 3 sigma, so all still sure enough. And then they assume there's also di-methyl-sulfide. And this di-methyl-sulfide is a an indicator for life, more or less. So people assume when you find di-methyl-sulfide, this planet probably has life, because chemical processes don't produce, the chemical processes we know on Earth don't produce a lot of this DMS thing. That's already an assumption, because we don't know the chemistry in such an atmosphere, and if it's not possible to do it without life. That's one thing. And the other thing is the DMS is not really so safe, as we will see in the critique on the next slide. But here we see the spectrum, and here we see the error margins around for the single gases. You can see for the CH2, they're really fitting well. And for the DMS data, and here for the DMS data, the error margins are relatively large, so the measurements are not so secure yet. And that is exactly the point, because CH4 and CO2 you will find in lots of atmospheres, and it doesn't mean anything interesting happens there. Although, I mean, 20 years ago it was science fiction to measure atmospheres of exoplanets. That shows already the progress we have made in the recent years. But fitting these gases to a spectrum is not a straightforward process. And the authors say they assume there is DMS inside the atmosphere, but critique came and said, listen, the fitting could also be done with propine in the spectrum, and propine could be produced in another way than life. And the other point of critique was, does the ocean exist? Have we safely proven that there's an ocean on this planet? The ocean itself does not hit the argument directly of the DMS, but the thing is, if you don't find water, if you look at the Earth, most of the DMS is produced by algae. So as a chain of proving life, the ocean is important, because if the DMS turns out to be correct, the next question would be, is there water? Is there an ocean where algae can exist, and is this actually algae that produced the DMS? So it's almost a second step. Is the ocean there? It's not crucial for the argument, do we find DMS or don't we find DMS? But it's a second step. Then the authors doubled down and made another paper, 2025, and said they used data from the MIRI experiment, so in the higher wavelengths, in the mid-infrared, or I would call that actually long wave infrared, but mid-infrared is somewhere here in the left part of this spectrum shown. And there they have found DMS, and a variety of DMS, which is DMDS. So the fitting is better, and they say even give an abundance of the gas, which is at least 10 parts per million volume of the atmosphere. So that is the result that has to be discussed now. Very interesting result. And this is another plot. I see that there's an error here. This is another plot, and there they fit methane, CO2, DMS and DMDS, and everything combined to the spectrum. But as of course, because these overlap, you're never perfectly sure if this DMS and DMDS part couldn't be done by other molecules. The thing then is a bit of a modeling question, because which gases are stable together under which circumstances, this kind of thing, but it's still a bit too difficult or too early to know this kind of thing, because the research just started about other atmosphere. But at least this is something that can be not only mathematically simulated but also made in a lab. You put gases together and see what happens if you have irradiance, if you have ultraviolet, if you have maybe lightnings. These kind of experiments have been done for tens of years now. So as a summary, are the data convincing? I think it's a bit early to say that. Can the spectrum possibly be explained by different molecules? That's one question to be answered. The other is a biomarker on the Earth the same as a biomarker on another planet? And this is something that this question also involves other planets in our solar system, specifically Venus, because on Venus also very important, very interesting gases have been found in the upper atmosphere. And then the question is, on Venus you don't have a lot of water and the chemistry is very different to the Earth. But is it possible that you have maybe bacteria flying around in the atmosphere or something? Or is the chemistry really responsible for the gases that we found in Venus? So maybe Venus is a first step to answer this question for exoplanets, because in Venus we can send probes there, we can make measurements. And the third question is, would the presence of an ocean add to the credibility of DMS as a biomarker? Life in another solar system doesn't have to look exactly like life on Earth. People think water helps. Actually, people look for watery worlds, and if they don't find water, they tend to discard a planet as bearing life. People think water is actually necessary. That's the critical test about Venus, because Venus is very dry. So this is just, I wanted to show you this as an example that infrared spectroscopy can be important for very important questions in not only astrophysics but also astrobiology. So thanks a lot for the attention.